Good afternoon, Nirmal sir. Hello. Nirmal sir, are you there? Hello. Hmm. Nirmal sir, can you hear me? Hello, Nirmal sir. Dr. Nirmal, are you there? Hello.
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 Hello. Am I audible?
Yeah, yes, you are audible, sir. Am I audible, sir? Can you hear
Yes, sir.
me?
Yes, sir. Yes, sir.
Okay, no issue. Can we start?
We can start. We can start, sir.
Just check your presentation, whether you are able to present here or not. Share your screen, sir, please.
Okay, okay. I am sharing my screen. One second.
Then I will introduce you. Then we will start. Okay.
Is it visible?
Yes, sir. Visible.
Okay,
Okay,
okay.
sir. No issue. Full screen mode. Uh,
Okay, we
so
can start.
now it is not showing, sir.
Yes, I turned off this for
Okay,
now.
turn up. Okay. No issue. You can turn on. No issue. Okay.
Okay, okay. We can start.
Okay. So, dear participant, and this is the second session of day two. We have our guest speaker, Dr. Nirmala Malik, with us. I want to introduce him to you. So, Dr. Nirmala Malik, Assistant Professor, Department of Electrical Engineering, Sonoka Education Trust Group of Institution, Durgapur, West Bengal. He holds both MTech and PhD degree in Electrical Engineering from renowned IIT ISM Dhanbad. With a specialization in power system and voltage control, he has over 6 years of teaching experience and served as head of the department from 2022 to 24. His research interests include dynamic voltage restorer, fuzzy control, power quality improvement, and renewable energy. He has several publications in reputed SCI and SCI journals, and he also a reviewer for international journals like IT Power Electronics and ISA Transactions. He has authored two academic books, published four patents, and active member of multiple technical and professional bodies, including IFERP and IAENG. So, sir, thank you for coming today. We are very much pleased to have you in this session.
Uh, Thank you. Thank you for this wonderful introduction. So, good afternoon to all. I hope you are doing well. So, it is an immense pleasure for me to be here with you today. And I'd like to thank GSIT for inviting me to this FDP. So, am I clearly audible?
Yes, sir. Clearly audible.
Okay. So let me share my screen.
Sir, share your screen. Okay.
Yes, sir. Is it visible?
No issue. You can continue.
Is it visible in full screen mode, sir?
Yes, yes.
Okay.
No issue.
So today I will be speaking on the topic of voltage quality issue using dynamic voltage restorer. And here we will see that how we can integrate our different subcomputing techniques while improving the power quality. So I look forward to sharing some useful insights and practicals aspects with all of you. So let's hope that the session will be informative. Now, as per, let me turn on the pointer first. Yes. So as we know that a power system is a highly complex system. It is all known to us because we all are electrical engineers. Because power system is not only just for generating electricity, but there are lots of layers included in it, like generation, from generation to transmission to distribution to finally consumptions. Okay, there are different kinds of consumers, different kinds of utility market are there. So it is a competitive market, and due to various equipment, large equipment, protective devices, compensating devices, they all need to be interconnected. Okay, so a power system, we can say a highly complex as well as interconnected system. There are so many advantages of interconnections. I am not going into it, but there are some disadvantages of this interconnection also. What are those? Suppose a problem occurs in one part of the system. Suppose in north there are some problems occurring. It may happen that it can affect the power supply stability in the south as well. Okay. Lastly, we can say that the power system is a sensitive technology intensive industry. Why? Because of the recently developed advanced control systems, real-time monitoring, different fault-tolerant designs, they are necessary. Because of that, even a small error in the control system, like suppose you can say that a miscommunication between sensor and circuit breakers, they can cause a huge blackout. So basically, this line that a typical big scale venture is called power system. Okay, it supports the backbone of the economy. So if somehow power system fails, our economy may fail. Okay, how? Let's say, uh, you know, as a consumer, we all desire basically that a good design of product. Okay, food also, good quality of food, but what are the backbone of this processing in various processing units, like in various manufacturing units? Electricity is main thing. If there are no proper electrical quality or no proper electricity is coming in terms of suppose frequency or voltage or current, or there are some sparks are there, it may happen that we do not get the exact texture of the product. It may happen. Then ultimately what will happen? Customers' interest are inside that thing. Okay, so there will be a huge financial loss. The manufacturing unit has to suffer to a loss. Like in this example, in a petrol car or diesel car, instead of petrol, if we fill like water, then what will happen? The car may gets burned out. Okay, it will not provide the exact mileage that it has promised to deliver. Like in EV electric vehicle, suppose the electricity is not good, poor electrical quality are there, then what will happen? The charging system may get damaged. The electric vehicle might not work properly. So as in critical care unit like ICU, NICU, ICCU, there are lots of devices like sensitive devices. Our lives depend upon this. Okay. If suppose somehow electrical failure occurs in the hospital, like in critical care unit, then we can't imagine what may happen. So ultimately, process shutdown, halt of production. Like currently I am working on a laptop. Suppose there is some problem in electricity, then what will happen? Like our data will be lost. So it is basically the loss of data, loss of time, ultimately loss of money. And we all know that to restart a big industry or big manufacturing unit, it will take a huge downtime. Okay, so it is found that the poor power quality is responsible for a global loss of approximate $300 billion. So it is a huge amount. Now I am talking about power quality. Okay, so let's talk that what is power quality basically. In IEEE standard or IEC standard, they have defined this power quality in their own way. Power quality basically refers to how well the electrical power supplied to our homes, businesses, industries, like consumers, with the ideal standard of voltage, frequency, and current, as well as waveform, as in desired form. That means what we desire, that must be received in terms of waveform, in terms of magnitude, in terms of proper phase, frequency, or power. So the utility system must ensure us that the electricity we receive, that is clean, that is stable, that allow our devices to properly work efficiently and safely. So like in this figure, we can compare the power quality as our heart. Just as our heart needs to maintain a steady rhythm to keep us healthy, like our electricity system also require a consistent voltage and frequency to function it properly. Deviation from that rhythm can lead to malfunctions or even damage, like our body. So now, what are the effects of poor power quality? Let's talk about now. First, suppose on equipment, if there are poor power quality, it may cause overheating. Like in case of unbalancing, we know there are overheating of rotor may happen, like neutral heating may be there. So additional loss, additional heating will be there. Motors will draw the more current that is than they are designed for. Okay, like electronics devices, we know that the PLC in automation or medical devices or our computers, there are small kind of sensors are there. They are more sensitive. Okay, they are beneficial but sensitive. Sensitive to what? Sensitive to poor power quality. So ultimately, if continuous poor power is being supplied to the system, then what will happen? The lifespan of the electrical appliances will reduced. Like on industrial process, we have already discussed that production may get halted. Okay, that will lead to increased maintenance and downtime cost. And in like power system, when the power quality is poor, the system becomes less efficient. Higher loss occur in the transmission and distribution. Suppose unwanted harmonics will be there. There might be overloading of cables and switchgear. It may happen that the protective device has to operate more often and increases the chances of fault. So ultimately, what are the goal? Our goal is to protect our system from the consumer side also, as well as from the utility side, that we need to protect by supplying good quality power. So in the next slide, coming to what are the basically needs of power quality. The first and most important reason is reliability of electrical system. Reliability means minimizing the downtime and failure. A continuous good quality of power to be supplied without any unexpected interruptions. So that is the main thing which is especially critical for hospital, medical emergencies, industries, data centers, even for homes. Next thing, energy efficiency. We need to reduce the unnecessary losses that might happen due to unbalancing, due to fault. Okay. So another major point is cost saving. Like when the power quality is poor, frequent equipment failure may occur, higher maintenance cost and system inefficiencies will be there. So we need to avoid penalties from utilities and reduce the need for repairs. Supplying proper power, proper electricity is also required from the point of utility, because this is the era of competition. If one company could not supply the proper power, proper electricity, then other players are there. So what are the different power quality issues? If we classify the power quality, then we may find that there will be a transients, impulsive oscillatory transients, like different steady state issues, under voltage, over voltage, voltage swell, sag, harmonics, notches, DC offset, so like this. Now, in our research, we will focus on compensation or mitigation of voltage sag. Why voltage sag is important among all other power quality issues. Okay, and before that, we may discuss that why voltage quality issues are mainly significant in terms of power quality. Power quality is also means that voltage quality, because the what we have studied, that the current mainly depends upon the load and voltage mainly depends upon the sources. Okay, but if there are some nonlinear loads are connected, it may happen that the distribution side, the voltage at the distribution side may get hampered. Okay, and there are also lots of voltage quality issues that have been found. Right now, among various power quality disturbances, voltage sag stands out as one of the most critical and frequently affecting both industries and commercial operation. It has been found that among all other voltage quality issues, almost 60% is voltage sag. Okay, so what is this? What is this phenomena? Voltage sag phenomena is nothing but the dip in magnitude of voltage, and the voltage magnitude will be from 0.1 per unit to 0.9 per unit, and the duration of this event will be 0.5 cycle to 1 minute maximum. Okay, what are the various causes? The various causes are suppose transformer inrush current, suppose starting of motors, as well as there are few external faults, external reason like faults also there. Okay, so now as we can see, what are the effects of voltage sag? Voltage sag, as we have already discussed, that it is one of the most common issue. So the effects are mostly economical. Now, suppose huge data loss, that already discussed. Huge data loss are there. Factory stopping of factory, also maloperation of our equipment. Okay, so same issues that already we are concerned for. So mitigation of this voltage sag is necessary. So how we can mitigate this issue, this voltage sag issue? By the use of custom power device, we can mitigate voltage sag problem. Not only voltage sag problem, but custom power device is also responsible for mitigating voltage swell, also different transient, different notches also. You'll also look into this. Now, what is custom power device? Like facts, custom power device is a device that is used at the end user side. It is to deliver the customized power for the customer. Okay, the customized power for the customer. Now, what are the various kinds of custom power devices? Like dynamic voltage restorer, it is one kind of active series compensator. There are shunt type compensator like D-Statcom. and also combination of both, that is UPQC. Now, what is a DVR? DVR is a series type custom power devices. The main components are, the main objective was to inject required amount of voltage to the system whenever required. Okay. The main components of these are the injecting transformer, the voltage source converter, controlling unit, and energy storage unit. Now, coming to the motivation for the present work. As already we have discussed that voltage sag, it is one of the common power quality problem. So we need to extensively study about the effects of voltage sag. The coming to the DVR, you know, this is a era of smartness or era of intelligent control mechanism. Okay, if we improvise our DVR control with the help of different subcomputing techniques, like suppose ANN, fuzzy logic, or any other optimization techniques, okay, then what will happen? Will our results get improved or not? Will our DVR be smart? Okay, let's see. And in another important area of focus here, the applicability of renewable energy storage system. Okay, this is also an important game changer for DC link support. So ultimately, here we will try to develop a robust, effective, accurate, smart RES integrated DVR. So let's see. Now coming to this study, this is the first study that we have done. This is a performance evaluation of a DVR using fuzzy based system. Okay. Here, one of the key objectives in this study is the significance of real power minimized DVR. Now, what is this thing? ESU or energy storage unit, the part of DC storage in the DVR that is required for the real power supply whenever the sag is occurring. Now, we know that the energy storage unit has high cost. Okay. So can we minimize the cost by reducing the size of the system? Yes, we can. And that has been discussed here for the DVR system. Okay. Also, we have examined the self-tuned fuzzy PI controller. That is one adaptive version of the fuzzy controller that is discussed here. And next, we have compared with the existing ones. So this phasor diagram is the basis of all our study. What is this? This is a V pre is a pre-sag voltage. That means is a normal quantity. V sag is a sagged voltage or the load voltage during sag. Now we can observe that the V sag is less than the V pre. There
Sir, you are not audible. Hello? Sir, is there any problem? Hello?
I think there might be some glitch, so don't worry. Yes, sir. Sir, you can resume with the slide, sir. Sir, you are not clearly audible, sir. I think there might be some bandwidth problem. Hello.
One
Sir, you
second,
can
there are
leave.
few network issues.
I understand. We understand, sir. It's not a big mark. So you can, if you think, you can leave and again join again, so that you will get a good bandwidth then.
Hello, currently am I audible?
Yes, sir. Now you're audible. Now you're audible.
Okay, okay. Basically, there are some real-time power quality issue here, so that is why.
Okay. Okay.
Uh,
Okay, sir. We understand. Okay, sir. Everything is
my
fine
screen
now.
visible? Okay, okay.
Yes, sir.
Okay.
Everything is fine. Please continue.
Okay. So this is the. Let me use my pointer. So if there are some voltage sag issue is there, VDVR will inject some voltage and it will again rectify the voltage magnitude. But we can see here the VDVR is almost in 90-degree phase with IL or load current. That means reactive power compensation will happen here, and the real power delivered from the energy storage unit will be minimized or maybe zero. So when the real power drawn from the energy storage will be zero, if this condition 2.7 is fulfilled. What is the condition 2.7? It is the Kc greater than cos phi. That means the sag factor, if the sag factor is greater than the power factor of the system, then the zero active power compensation will happen. Now, what is sag factor? It is nothing but the per unit load voltage during sag. Suppose for an example, as an example, our system has a power factor of 0.8, and right now there is a voltage sag, and due to that sag, the voltage amount is 0.85 per unit. Okay, so 0.85 is Kc and 0.8 is the power factor. So equation 2.7 is satisfied. The DVR need not transfer any power from the energy storage unit. Okay. Now, if the voltage sag occurs in such a way that the voltage magnitude gets reduced from 0.8, that means suppose the load voltage is 0.75 and the power factor is 0.8, then equation 2.7 will not be satisfied, but it need to follow equation 2.6, and by that a minimum power transfer mode will be there. That means a minimized power from will be delivered from the energy storage unit. But there is a catch. Can we extend this equation 2.7 to some extent? Like suppose power factor was 0.8 and voltage deviation okay. So can we reduce the power factor from 0.8 to 0.72 so that equation 2.7 is also valid? Yes, we can do it. By how? We will follow here the algorithm of power factor reduction. That means we will add some inductive load in parallel with the existing load, so that the switching of the inductive load will be such that the power factor of the whole system will be reduced and the power drawn from the ESU will be zero. So we will get our energy storage unit size will be more reduction. We'll have more reduction in size as well as cost, as well as there will be an increment in the lifespan. But is it easy to connect inductive load to with the existing system? No, there will the effective loads or the net load will affect the grid. The grid balancing may get hampered. That's why the amount of inductive load needs to be balanced in okay. And we will observe our results that what we have done, is it actually beneficial? Okay, we'll observe that thing also. Now coming to the fuzzy based control algorithm. Okay. Here we have used a self-tuned fuzzy PI. Suppose for an example, I am working in a process control unit as an employer. Okay. In that process control unit, there is a there is a system that is automatically produce some output based on some input. But I, as a human operator, need to change that output or need to modify that output to some extent. What we will do? We will add some data and the net output will be changed. This thing is modeled with the fuzzy PI controller. There is one single fuzzy PI controller. There is output. The input of the fuzzy PI controller is the error and change of error. And there is the output of the fuzzy PI controller, that is the change of control unit. Okay. Now, if that change of control unit is multiplied by some gain updating factor, and that gain updating factor is also depending upon error and change of error, if we do so, then our fuzzy system will be more adaptive. We will see the block diagram in the next chapter. And why we are doing this? Because we know that the power quality problems or the real-time problem is not a linear system, but it is a higher order and higher degree of nonlinearity will be there. There will be a data ambiguity, there will be a uncertainties are there. So we will do this. Now coming to the proposed control strategy for this system, there is a proposed control strategy equation. As what we have seen, that there are various equations. With the help of those equations, we developed VDVR Q and VDVR D. These are the references voltage, and thus adaptive fuzzy controller are used. One controller is used to regulate the DVR losses, and another controller is used to regulate the load voltage. Okay. So these are the membership functions for the self-tuned fuzzy PI controller. And this is the rule base. Like in this rule base, if suppose error is PB, positive big, and change of error is positive big, we need to have a positive big of change of output. But if we multiply this positive big with some very high value, then the output will have a significant one. So this control system is used as a control unit to the voltage source converter, and this is the whole test system. Here we have introduced we have enforced some fault in different branch. Like here we have a sensitive load, and with that sensitive load we connected a DVR. There are some faults, there are some induction motors. We will observe what are the effect of starting of induction motor. And as an ESU, we have connected here the battery storage unit. Now see in figure 2.5a, if we observe, or also we can see the 2.5b also, if we use the proposed method, that is the reduction for power factor method, then we can see that the VDVR for proposed, the compensation capacity is increased compared to other existing ones, whereas the power delivered from the energy storage unit or power required from the energy storage unit is less compared to other ones. Same in figure 2.5a, like PDVR for power factor 0.6, it is less than that of the other one, whereas the DVR voltage or compensation capacity is high. Same in figure 2.5c, like for 0.5 sag factor, this yellow one is the DVR power or power required from the energy storage unit, and it is very less compared to the other ones. Now there are different scenarios that we have studied, like starting of motors at different point of time. There are different symmetrical or unsymmetrical fault effects. So let's see our results. This is the voltage profile of load, the first one 2.6a. We can see that in this portion the motor, starting of motor occurs, and due to the starting of motor, one V-shaped voltage sag will be observed. Okay, and in this portion the symmetrical fault is there, and due to that almost rectangular type voltage sag will happen. Okay, at the instant when this is going on, at that instant the DVR will ready to supply the required amount of voltage, and this is the voltage that is being supplied to the voltage dip occurred due to the starting of motor, whereas in this portion this is due to the fault, steady symmetrical fault. Okay, and this is the load voltage. It is almost regulated load voltage, and this is the DC voltage, regulated DC voltage. Here also pertaining to unsymmetrical fault, we may observe the results. This is the unsymmetrical fault case, and the load voltage is compensated load voltage. Now if we observe the present technique with compared to other technique, that the required DVR power is less. From simulation we have found out that the our study supports our proposal. So in TSD comparison also, the proposed controller, the system TSD is very less compared to the existing studies. Now as per soft computing technique, in the previous study we have discussed the type 1 method of fuzzy logic controller. Now we will move towards the type 2 fuzzy logic controller in case of power quality system. What is type 2 fuzzy logic controller and why we are moving to it? In power quality system there are, or in power system basically, there are loads uncertainties. Okay, also if faults are there, data uncertainties are there, ambiguity in data will be there, especially voltage sag, harmonics, transients. In that case the data are rarely clean or rarely predictable. We may face noise from sensors. There may be environmental effects like electromagnetic interference. There may be load variability. So in real world system, if we move towards the type 2 counterpart of type 1 fuzzy logic, then it may happen that the results will be much more smoother. Let's see now what is type 2 fuzzy logic system. Suppose for me, hot in the temperature set of fuzzy, it is 0.7, but to some other person it may be that 0.8, or to another person it may be that it is 0.6. So in type 1 fuzzy system, like type 1 fuzzy system, the membership function is not a crisp value. Instead of crisp membership function, we are making the type 1 fuzzy membership function as a itself fuzzy. Okay, let's see here. Now this is the implemented control strategy that is used in this case. The control strategy almost similar to the previous one, but different is that here it is, we have used the single phase study, and instead of the type 1 control technique, we use adaptive type 2 PI fuzzy logic case. Now that words can mean different things to different people. So that was the motto to develop the type 2 fuzzy logic counterpart. This type 2 fuzzy logic counterpart, the membership function are itself fuzzy, thereby adding additional degree of freedom. So we are basically enhancing the fuzziness into the system to deal with the uncertainty of the power quality problem. So here we have used the interval type 2 fuzzy logic for simplicity, and in this case this is the like in 3.2, this is the membership function of type 2 fuzzy case. Here not a single triangle like in type 1 fuzzy, there is a single triangle, there will be a single triangle. Okay, but in type 2 fuzzy logic there are like lower membership function as well as the upper membership value is there. Okay, and this portion is making our system or enhancing our system fuzziness. And in calculation part, In type 1 fuzzy system, we have fuzzification, there are inference engine, as well as some defuzzification technique. But in addition, in this case, there are type reduction unit, which is slightly complex. However, we are making it like in the previous case, adaptive. Okay, what was the adaptivity? Here, the block diagram is shown. Like there is one type 2 fuzzy logic. The output of this fuzzy logic control is change of control system, change of control output. Okay. Now another fuzzy logic is used. The inputs are same current scenario, but the output is the gain updating factor, which is working as an human operator, and he is providing the input to the manufacturing unit. Okay, and this eta or gain updating factor is getting multiplied, and this is the net output. Here also the membership schematic structure is given here. This is the schematic structure of for input, and the rule base, the similar rule base like type 1 is used here. Like for PB error and PB change of error, we need to have a positive big change of control system, whereas the very high. One thing, if human expertise is little less in any fuzzy logic system, the type 2 fuzzy logic may handle that uncertainty also. Now here in this system, we have used hybrid energy storage system in terms of DC storage. What is this? Why we are using this hybrid energy storage system? Because we are hybriding here the battery along with the supercapacitor. Why we are doing this? We know that the battery might be used for long-term voltage sag, okay, because it has high energy density, but due to some chemical reactions, it has slow dynamic response. But DVR is a system that required to supply instantaneously. For that case, supercapacitor, in practical scenario, supercapacitor may help. Right? Supercapacitor has a very fast discharging time as well as charging time, so it can rapidly work. But problem with the supercapacitor is that it has high power quantity density, thereby it may not provide a prolonged voltage sag issue. Or suppose if there are any under voltage issue, the DVR with the help of only supercapacitor, the DVR may not work. So to reduce the limitations of both the energy storage unit, we can hybridize them. And to hybridize them, we have used here a modified bi-input, bi-output, bi-directional converter. Okay, there is a battery storage and string of supercapacitor. They are connected with some power electronic switches, and those switches are controlled like the battery. The switches for battery are controlled to control the power sharing in between them, whereas the switch of the supercapacitor is controlled to regulate the DC voltage. Okay, so this is the Vivo DC-DC converter control. Here, as already discussed, that switch T1 is controlled to control the power sharing between the battery and the supercapacitor, and the control is ANN is used. ANN is trained by the demand power as input, and the output was and the target was the gains, PI gains. So this is the test system. The hybrid energy. One thing is that in this Vivo converter, there are bi-output level. That means at one level, suppose at NO, we may connect our DVR, whereas at another voltage level, we may connect some DC load. That we have simulated here. At one level, we have connected some DC load, and at another level of voltage, we have connected our DVR. So these are the results and observations. At 0.1 second, the voltage sag is enforced, and there is some phase shift is also there along with the dip in voltage magnitude, and instantaneously VDVR provides its result, and the compensated voltage is almost the load voltage is almost compensated. And this is the various voltage signature of like DC voltage at two different level. this is the energy storage unit voltage, and this is the power sharing between the battery and supercapacitor as well as to the DC voltage, and this is the power required to compensate the load voltage. Now in this case also we have with the help of in comparison with type 1 fuzzy logic, we have compared our proposed controller, and the voltage regulation is slightly higher, but it is good, and PSD percentage is reduced. So in this case, we have moved another subcomputing technique, that is type 1 fuzzy logic to type 2 fuzzy logic. Okay. So in the next case, renewable energy storage renewable energy system in terms of PV, okay, that is used. Here also PV arrangement, there will be a hybridization of two different subcomputing technique. In the DVR also an optimization techniques, that is a student psychology based optimization technique, is incorporated. Let's see. This is the implemented test system. Here this thing is the whole energy storage unit. Okay, in energy storage unit, for the sake of avoid limitations, we have used a supercapacitor with the help of charge controller to regulate the DC link voltage, whereas a PV arrangement was there. In the PV arrangement, we try to obtain the maximum power delivery from the PV with the help of a hybrid artificial network integrated with a type 2 fuzzy logic system. Okay, but here we have used another type 2 fuzzy logic system. It is closed loop type 2 fuzzy logic. Okay, and in the control unit, let's see the control unit of the DVR, because it is the heart of the DVR, the core of the DVR. Here a simple control technique is used at first, like the DVR reference, the measured value is compared with the reference one, and it is turned into it is delivered to the PI controller, and then the value is obtained. But the PI controller, it is optimized with the help of student psychology based optimization technique. That is another subcomputing technique. And why did we use this student psychology based system? Because it is recently developed. It was one of the recently developed technique. Also, the advantage, the benefits of this system is that it has no adjustable parameters like other ones. Also, it was found that if the population size is small, like 15 or 20, then also it provides a better results. Okay, it is based on the psychological behavior of the students. Now this student based psychology optimization system is providing the optimal PI value, whereas to make it more real time oriented, we are replacing the whole system with the help of a neural technique. The optimal control, where the inputs are various sag scenario like sag depth and associated phase shift, whereas the output is trained with the optimal DVR value or SPBO optimized DVR value. Okay, so real time. Now coming to the energy storage unit part. Here closed loop type 2 fuzzy logic system is used, where it is different, slightly different from the interval type 2 fuzzy logic that was seen in the earlier section. In the interval type 2 fuzzy logic system, we have observed that there is one block. It was called the type reduction block, and due to that the system is becoming more complex. In this closed loop type 2 fuzzy logic system, the inventors has developed the system in such a way that type reduction method is getting bypassed. Okay, so that makes our system more simple. Now coming to the energy storage unit, how we are obtaining the maximum power from the PV, but under partial shading condition. Okay, here we have connected 3 solar modules in series, and these are under different irradiations. Okay, suppose in one set of irradiance level, the maximum power is at zone 2. Okay, or it may happen for another set of irradiation level, the maximum power is at zone 3 or any other zone. Okay, if the number of modules are increased, then with that the zone will be increased. But here the technique we have used, one artificial neural network technique is implemented for zone selection. Okay, and if the zone is selected, suppose the maximum power currently is in zone 2, then zone 2 will activate the closed loop type 2 fuzzy logic controller of the system, and the inputs of the closed loop type 2 fuzzy logic are change of power. Change of power means with the reference one in compare with the measured one, and change of voltage, and it will try to obtain the maximum power at that zone. Okay, so these are the membership functions for PV MPPT. These are the rule base for PV MPPT system. And now coming to the result section. In result section in 4.6a, we may find out that we have the voltage sag occurs, and this section B, the voltage sag due to the induction motor starting, the V type voltage sag. And these are sketches of VL, or we can say the results after DVR performance. Now coming to the effectiveness of our control system that we used in the MPPT technique. Okay, there are different cases of irradiance level. At one level, this blue section is the maximum power. At another level, this black portion is the maximum power. Whereas at another level, we have found that this is the red section of them is the maximum power. And in each and every cases, our technique achieved the maximum power very fast, as well as with very less ripple compared to the existing one. If we compare with the existing methods, that the tracking time is much more faster. Okay. Now, this is the sketches of VDC, DC voltage. These are the various examples of convergence plots. And the performance indices like voltage sag, lost energy index, or Detroit Edison sag score, the compensated score is very less. That means our system has performed well. So here, what kind of techniques we have used? We have used an advanced version of fuzzy logic that is integrated or hybridized with a neural network, and we have obtained our desired results. And also a student-based psychology optimization technique was discussed. Now, due to recent breakthrough in electrochemical technology, there is a fuel cell or proton exchange membrane fuel cell. If we use this in our DVR system, then we will see what will happen. Okay, because it is a very clean carbon-free source. It is an environmentally friendly source. Okay, so in this study, we have incorporated a PEMFC, as well as we try to achieve the maximum power from that source also. Let's see. So this is the implemented control strategy. In the energy storage unit, there is one single source, that is a fuel cell. That fuel cell is connected with a bi-output DC-DC converter, and a closed loop type 2 fuzzy logic is used here to obtain the MPPT, as well as to regulate the DC voltage. And there is another control section. There is one detection scheme, means what kind of voltage anomaly is occurring. Is it voltage sag, voltage notches, or phase angle alteration? We may add here other also, like any other transients or voltage outages, voltage swells also. This is the implemented control strategy. This study was made earlier. That is why here we have used the Gray-Wolf optimization technique to find out the optimal PI values. And here the gain updating factor is the output of one closed loop type 2 fuzzy logic controller. Okay, here similar study is done, like similar of our first study or second study, like the human controller is trying to manipulate the output of the system, like the human controller here is modeled by the closed loop type 2 fuzzy logic, and the system is modeled by the optimal PI controller. So this is the ANN block that is used here. Also the optimal PI gains are the output or the target, and the inputs are various voltage sag scenario. Now we have already discussed about the closed loop type 2 fuzzy logic system, and let's see how we can implement it to deliver or to achieve the maximum power from the fuel cell. Here it is the characteristics of a fuel cell, which is slightly different from the PV one. Here fuel cell power and current characteristics are given here, and this is the MPPT. The control block is presented here. The input of the control block is change of fuel cell power, and instead of voltage here the input is the change of fuel cell current, and the output is the duty cycle. And these are the various membership functions that was used. And the DC voltage regulation strategy, the error and change of error are the input of the type 2 fuzzy logic system, and the duty cycle is the input of this DC-DC converter by output DC-DC converter. So these are the rule base for hybrid control system, and these rule bases are found experimentally. And this is the PMFC MPPT control rule base, and this is the rule base for DC voltage controller. So here it is the studied test system in a schematic diagram, and also here in another line fault occurs, as well as some DC load is connected with a controlled rectifier, and we'll find out that what kind of notches are there, if there are harmonics. Okay, so these are the simulated results of our voltage profiles during SAG, and we may find out that there are a few notches are there. The voltage sag might be visible clearly. This is the voltage profile of DVR during sag and during the whole time, and this is the output regulated voltage of the system. Due to somewhat slow response, the initially regulated voltage is less, but we may in future we may integrate some hybridization with the fuel cell, so that this can also be mitigated, because a small amount of voltage dip is very dangerous. So this is a comparative study of the proposed MPPT algorithm with the existing ones, and it is visible that our study is faster and also very less ripple is there. And this is a profile of fuel cell power during sag scenario. Now, if the phase angle deviation is detected only instead of voltage sag, our DVR also can prevent our system from any deviation of phase shift also. So this is the during outage. Suppose our DVR system not only voltage sag, but if there is any under voltage or voltage interruption for a prolonged time, it can also regulate the system, regulate the load voltage. Okay, these are the example convergence plots during the scenario of phase shift. Basically, in ANN controller, to achieve the inputs at different sag scenario, we need to run our GWO multiple times. So these are the sample for that against that multiple times running. Now, in the earlier study, we have found the voltage regulation values and TSD regulation value. Here, our proposed controller effectively provides the voltage regulation value as well as effectively reduce the total harmonic distortion in percentage. Now coming to future work, so this is one part of our study that we have discussed. Our study is also going on. So there are lots of subcomputing techniques are coming, like ANFIS is already there. we can modify our fuzzy logic core system. Okay, we can also instead of proton exchange membrane fuel cell, we can also incorporate any other DC energy storage units. There are many hybridization like IPFC is there, interline DVR is there. So there are those might be in the future work. So these are the references, and thank you from my side.
Thank you, dear speaker, Dr. Nirmal sir. Now it's time for the question answer session. Participants are requested to kindly on your mic, and you can directly ask the question to the speaker. No issue. If you have any question, kindly unmute your mic and ask this question to the speaker.
Hello.
Yes, sir.
Actually, this topic is a part of utilization of soft computing techniques in a power quality improvement studies. There are lots of other studies are going on, and I request all the participants, those they must look into this portion, because it is one of the trending topic, we must say, because renewable energy sources are there, AI is there. So this is not a saturated part. Any questions you can ask me?
Dear participant, kindly, if you have any question, kindly unmute your mic.
Hello. Hello.
Yes, sir.
Yeah. Can you hear me, sir? See, sir, in conventional system, we have this voltage sag and all those things. And now we move more towards renewable energy. And from your expertise, can you give any idea on the voltage sag and all those issues with respect to incorporating more renewables?
Hello, am I audible?
Yes, sir. Yes,
Yeah,
sir.
audible.
Yeah. See, in power quality, different power quality system like voltage sag, transients, we are moving towards modern equipment right now. Okay, like adjustable drives or various kinds of power electronics equipments are there, solid state devices are there. Okay, those are, we know that those are very advantageous, but due to nonlinearities, they itself provide different kinds of power quality problems. Okay, but just with the use of battery or supercapacitor, we can compensate those things also. But if we use the renewable energy system, then what will happen? Now, suppose the cost of battery is high. If we use the renewable energy system, then two things may happen. One is to supply to regulate the load voltage, as well as we can obtain the other work. Okay, because like the size of the reduction, there will be a size of the reduction in this thing. Like in our study, that why we are moving towards the renewable energy system, why not only battery? Because it is a trend, and I think we must follow that trend. No?
Fine, sir.
Is there any question? Dear participant, is there any question? Nirmala sir, I think there is no question. So thank you for coming in this session, and your valuable talk in EV system and technique behind this is really we have learned a lot. So thank you very much for this type of session.
Thank you for having me. Thank you, GSIT.
Okay. Thank you, sir. I have already sent the feedback link. Kindly fill up it within 5 minutes. Then I will leave the Google Meet. I have already sent the feedback link to chat. Kindly check it. Okay. Thank you all. We'll again meet tomorrow.